Basic probability models. The probability of any outcome of a random phenomena is the proportion of times the outcome would occur in a very long sequence of repetitions. The sample space of a random phenomenon is the set of all possible outcomes. An event is an outcome or a set of outcomes of a random phenomenon. It is a subset of the sample space. A simple event is an event consisting of exactly one outcome. To compute the probability of some event E occurring, divide the number of ways that E can occur by the number of possible outcomes in the entire sample space S. So the probability of E is equal to the number of ways that event E can occur divided by the number of ways that we have in the total sample space. Basic rules of probability. All events have a probability between 0 and 1. All possible outcomes together must have a probability of 1. The complement rule says for any event E, the probability of E's complement is equal to 1 minus the probability of E. The addition rule says if E and F are disjoint events, remember, disjoint events are events such that their intersection is equal to the empty set. So they have nothing in common. So the probability of them both occurring would be 0. If this is true, then the probability of E or F, E union F, would be the probability of E plus the probability of F. Union can also be referred to as an OR statement. And when we have that, we use addition for our probabilities. If E and F are any events of an experiment, then the probability of E union F is equal to the probability of E plus the probability of F minus the probability of their intersection. Notice that this also applies for number 4, because if they are disjoint, then the probability of E intersect F is 0, since disjoint events have the empty set in common. Example 1. Suppose we draw a single card from a deck of 52 fair playing cards. Well, first let's look at a deck of 52 cards. So I've copied and pasted an example of 52 cards down here at the bottom. We have 4 different suits, and for each suit there's 13 different cards. I want to know what the probability of drawing a heart is. So here are my hearts. There are 13 different hearts. The number in my sample space is 52. We have 52 single cards that we could possibly draw. The number of hearts, heart will be my event here, is 13. So the probability of drawing a heart would be the number of hearts divided by the total in my sample space, which is 1/4. For the probability of drawing a queen, the number of queens that we have available would be 4. There's 4 queens in a deck of 52 cards. So the probability of drawing a queen would be 4 out of 52, which is 1 out of 13. Example 2. Here we have 5 marbles drawn at random, all at the same time from a bag. The bag has 8 white and 6 black marbles. What's the probability that we will have 3 white and 3 black? Well, first, how many possible combinations do we have for the sample space? What is the number of outcomes for my sample space? Well, we are drawing 5 marbles from a total of 14, 8 plus 6 marbles. Our order doesn't matter, so this will be a combination. 14 choose 5 is 2002. So the number in my sample space is 2002. Now we need the number in our event. Our event is choosing 2 white and 3 black marbles. From our counting section, we know that this can be computed by 8 choose 2 and would be multiplying 6 choose 3. We have 8 whites to choose 2 from and 6 blacks to choose 3 from. 8 choose 2 times 6 choose 3 is 560. So the probability of 2 white marbles and 3 black marbles is 560 out of 2002. This reduces to 40 out of 143, or approximately 0.28. Example 3. The qualified applicant pool for 6 management trainee positions consists of 7 women and 5 men. This makes 12 total people that we're choosing from. We're choosing 6 from this management pool, so the number in my sample space would be 12 choose 6. Again, we're using combinations since we do not have order as a factor here. So the total number in my sample space is 924. What's the probability that a randomly selected trainee class will consist entirely of women? So that would mean that all 6 chosen trainees will be from women. So the number in my event, which my event would be having all women, will be 7C6, which is 7. So the probability of all women is 7 over 924. What is the probability that a randomly selected trainee will consist of an equal number of men and women? Well, with 6 trainees, that would mean 3 men and 3 women. So the number in this event, so the number of ways that we can have 3 men and 3 women, would be 5C3 for the men and times 7C3 for the women. This comes out to 350. So the probability of 3 men and 3 women would be 350 divided by the total in my sample space, which is 924. This is approximately 0.379. Example 4. A sports survey is taken at U of H, University of Houston, and shows that 48% of the respondents like soccer, 66% like basketball, 38% like hockey. And then we're given more information about who likes more than one sport. So we want to find probabilities based on all of this information. First, we want to do it by using the formula. So let's look. What's the probability that a randomly selected student likes basketball or hockey? Let's let basketball be event B. Hockey be event H. And S in this case will be the event for soccer. So the probability that they like basketball or hockey will equal, by my formula, the probability of basketball plus the probability of hockey minus the probability of both basketball and hockey. Well, 66% like basketball, 38% like hockey, 22% like both. This gives me 82% liking basketball or hockey. The next question is, what's the probability that someone does not like any of these sports? Now this is best solved with a Venn diagram. So let's draw a Venn diagram here. We have three different sports, so I'm going to make a rectangle with three circles inside. One for my soccer, one for my basketball, and one for my hockey. Now when you're creating the Venn diagram for all of this information, always start with the inside and work your way out. So I'm going to start with the 12% like all three sports and put that right there. Then I'm going to do the combinations, for instance, 28% like soccer and hockey. Soccer and hockey overlap right here. Here's my overlap for soccer and hockey. And I've already got a 12% there. I need that total overlap for soccer and hockey. In fact, here, let's draw it right here so you can see. Here's the soccer and hockey right here. This total has to be 28%. I already have 12%. So 28 is equal to 16% plus 12%. Now I have a total of 28 overlapping the soccer and hockey. Okay, we have 22% that like basketball and hockey. Basketball and hockey overlap right here. This is 22%. I already have 12% in here, so I need another 10%. And last, I have 30% with basketball and hockey. So 30% is going to go right in here in this yellow. Again, I already have 12% there. So I need to fill that in with 18% to make the 30%. Last, we need to do the individuals. So 48% total for soccer. So I'm looking at this entire circle for soccer. I have 18 plus 12 plus 16. That's going to be 46%. That leaves only 2% not covered. For basketball, we should have 66. So 18, 12, and 10 are already in the basketball circle. That's 40. So I need 26% more right there. So that means 26% like only basketball, nothing else. 38% like hockey. Let's see, that's 28. 38, we already have 38% in the hockey, so there's nobody that likes only hockey. Now to figure out how many don't like any of the sports, I add up all of these numbers and I'm going to subtract from 1. So I had the 0.02 to the 0.18 to the 0.12, 0.16, 0.10, and 0.26, and that leaves me with 0.16 floating out here that do not like any of them. So we have 0.16 or 16% of the students that don't like any of those sports.